I've been asked on the second item on exam 4 to give a different approach. I used the beam table approach and superposition and manipulated that around to make that what turned out to be actually a lot easier to do. And some of you said, well, hey, I did the integral approach. Okay, I get it that if I can use the beam tables, it's a faster approach, but I wasn't confident that that was okay. So I tried the integral approach. Can you show me the precise way to do that? Because I saw that you marked that it looked like I attempted to do some things that even though I got the same answer, it just wasn't quite the same, and I'm confused, and just help me out. So that's what we're going to do here, is to talk through this using the integral approach. And there's no doubt this is a much longer and more difficult, time-consuming, and detail-oriented approach where there's a lot more opportunities for mistakes. So let's see how it plays out. What I did first off with the integral approach was just to take a look at what equilibrium told me and to see if it was going to be easier to do a double integral approach or the quadruple approach, right? And so that's what you're seeing here is why I did this. I went and found the reactions, right? And then just showed them the way they physically acted, drew the shear diagram, drew the moment diagram, and I look at that and say, yuck, that's not easy to do with one equation. In fact, it's not, you really can't do it unless you do something very fancy and sophisticated using singularity functions or discontinuity functions. Those are technically two different things. This would really be discontinuity functions, but some people call them the same things. The problem with that is it's an advanced approach, and only theoreticians will ever use that approach when it comes right down to it. Practicing engineers are going to draw these shapes, and then they're going to either use other techniques or they're going to look at those and observe from them what the equations are. And we can do that to some extent, not too badly. For the shear diagram, it's actually pretty easy, right? We have a constant region there, and that makes sense. There's no distributed load, so whatever the shear is, it's constant in that region. But when we get out into the outer portion where we have the uniformly distributed load, well, then it's just a straight line expression, right? So yes, you can integrate the load and you get a negative 0.3x, and then you have that constant of integration. And so then you've got to evaluate the boundary condition, which will be way out here at point A, where we know that the shear is 0, and that's what's going to give you that constant of integration here. So again, by observation, you could actually write those two. Now, that's not so obvious for the moment diagram. It's not too bad for the first part of the moment diagram, because it's just a straight line. But that second order piece that's out here is certainly not so easy. And so the straight line portion, the 6.2x minus 52, well, it's a straight line. Plug in the two numbers and see if you get the correct values. Putting in a 0 here will give us a negative 52. That negative matters, right? So it's a frowny face over here that shows up in the moment diagram in the US designer sign convention as a negative value right there. And that's what we get. And then if you put in 8 into here, you'll have 8 times 6, which is 48, and then 8 times 0.2 is 3.2. You get that in there, you'll get a minus 2.4, which is what it should be at those two locations. Right now, this expression here wasn't written by observation at all. It was done by just simply integrating the shear equation, and that's where we got minus 0.15x squared, right? X goes to x squared divided by 2, so that's where the 0.15 comes from. And then we got 3.6, that constant goes to 3.6x when we integrate. And then we got this constant of integration that we have to solve for. And there, for this region, the boundary condition would be way out here. You could use the continuity condition of minus 2.4 at x equal to 8. You could solve it that way. I did it both ways. I did the boundary condition, the moment out here at the far right is 0. And so what does that constant need to be when I put x equal to 12 there? And then I checked it to see if I got the minus 2.4 value here. And many of you who I think probably tried to use a discontinuity function didn't indicate that. And if you evaluate what you wrote down on the page directly, you will not get the correct values. You wrote one equation and put x equal to 0 in it, and you're not going to get this minus 52 value. You might get this region out here correct. I'm not so certain about that either, because Your version of this was written in an entirely different way. Now, you could play funny, interesting games of resetting the coordinates out here. You've got a parabola that has a vertex at x equal to 12. So you could do a funny little game there if you want. But if you do that, then you've got to be very careful about how you specify your domain and specify the different types of x's. And there was no one who did that. So when you just look at the base work that's on the page, you have to say, this isn't quite right. There's not enough information to take what's there and say that that is exactly correct and what the intent of that is. A lot of ambiguity there. So this sets this up correctly in a way. It's not the only way, but it is correct in its fullness. From there, we take the moment and we're going to divide by EI to get curvature, and then we can integrate to get slope. Right now, a little bit of word of how to process this. EI was constant along the beam length, so why not take it out of the integral and then take it over to the other side so that this is all easier to work with and to perform the calculations. So EI theta then is equal to the integral of moment times dx. Now critical, let's look at the units. Moment has units of force times length, and of course dx is an actual length. So this whole integral expression then has units of force length squared. That should make sense because EI also, as a combined thing, has units of force length squared, right? E has units of force over length squared. I has units of length to the fourth. So work that out, you'll get force length squared. Same thing on either side. Force length squared divided by the EI units of force length squared, that's non-dimensional, which is exactly what we've got here. Theta is an angle in radians. So that all works out from a unit standpoint. Right, so all we do is we integrate piecewise here our moment equation, right? After we take that EI over here, we just integrate that. We'll get a constant of integration on each one of them that we're going to have to deal with, right? And so the way you can deal with that is first go to the boundary condition. At the fixed end, that would be x equal to 0. We know that the slope has to be 0. And indeed, that moment of minus 52 is exactly the moment required at that location so that that rotation is absolutely 0. That's the meaning of a support force. It's not just equilibrium. It's also so that a specific displacement has a specific relationship. In this case, 0. Right? And so we put that in there and we find out that C1, when we put in x equal to 0 in this first equation only, and it has to be that one, that C1 is going to be equal to 0. Now, when we get to dealing with the C2, we don't have any boundary conditions to work with. All we know is that when we look at those two functions, that when we look at the slopes right at that location, they have to be identical. There's no hinge in the structure that would create a break in the slope. The beam is still performing elastically based upon our base assumptions about all of this work. And so it has to be nice and smooth and continuous. So the slope from the left and the slope from the right must be the same right here. In other words, take this expression, evaluate it at x equal to 8. Take the second expression, evaluate it at x equal to 8, that interface between those two, set those two equal to each other, and solve for the unknown, which in this case tells us that C2 is equal to minus 134.4. That has no x attached to it, so its units have to be the same units as EI theta, which we now know from up here that those are units of force length squared, which we've been working with kip and feet, so that would be kip feet squared for the units on 134.4. This whole thing is called a continuity condition, that we have to have continuous slope right through that region, that the same value, however we approach it from either side, has to be identical. So that gets us the slope. Now we're going to do the exact same thing for the displacement, right? Well, displacement's equal to the integral of the slope. Again, put the EI in there because it's easier to work with it this way. And note what we get here, that we have units of EI theta that are force length squared and units of dx, which are L, so that whole thing would have units of force length cubed, right? And EI itself has units of force length squared, so FL cubed divided by FL squared will give us units of length, A transverse displacement, exactly what we want, right? So again, we integrate our two slope equations now, and we're going to get two additional constants of integration. We've got two different regions, right? And we use the boundary condition, which says that the transverse displacement at that fixed end has to be 0. That's that shear value that was sitting there, a 6.5 kips, or 6.2 kips, that is, that keeps that from moving up and down. And that's exactly what it does. No transverse displacement. And plug that into this first expression, it tells us that C3 is 0. Right? When we then go and look at the continuity condition, that is that the transverse displacement from the left and the transverse displacement from the right, from these two different expressions, right, from these two, have to be the same. That's our continuity condition. And so we're setting the first one equal to the second one, and we'll have an equation just in C4, right? Not the explosive, but just our fourth constant out of all this. And it's going to have those units of kip feet cubed, right? You can see it also from the 134.4 had force length squared. 8 feet would be length, so force length cubed. All of these quantities have to end up with the same exact units. Okay? All right, so now we finally go and then calculate our displacement at A. We found what C4 is, right? We had previously found what the C2 value was, and we just evaluate that expression at the end, which is at x equal to 12, plug all that in there, and we end up with a value of minus 20, 14.9 and some change kip feet cubed. That's EI of the displacement. We really want just the displacement at all, itself that is, so we're going to take that number, divide by EI. There's our units that we've been working through, and I got rid of the minus sign and just showed the arrow or the direction of which way this would go, which should be pretty apparent. After all, we just have a cantilever beam with only a support out here at the left. All the loads are acting downwards. So of course this wants to then bend in a concave down kind of fashion. And so it'll have non-zero moment all the way through. We see that here. It's frowny face, and it's largest at the left and gets progressively smaller. So the radius of curvature starts out the tightest over here at the left and gets largest as we go all the way over. And there is our delta A that we were seeking, that we have found here. Again, you may have found almost an identical value, but you didn't get full credit. Why was that? It's entirely because of the documentation on the page wasn't clear what you were doing, and the equations that you showed were, well, they were incorrect the way they were shown. And to the point where it was confusing. Well, what does this even represent? What is this author trying to tell me of what they're doing? If I take it literally as shown on the page, not reading into your mind, but shown on the page, and plug in appropriate numbers, we don't get the right values. We don't get zero slope and zero displacement. You might get some of the constants to be the same, and I think it was just happenstance. If I do try to read into what I think you did, I think you probably used discontinuity functions, I think, but I don't really know that. And of course, on this test, we only had two techniques. The integral method and the superposition method were our two basic methods for finding our beam displacements. So anything addition to that was, well, it was outside of it, and that was sort of not within the realm of what you were asked to do this semester, right? Next semester in the structural analysis class, you'll find out a whole lot more other approaches in there, a lot easier than what we've shown here. You got a hint of that using the beam table, but even that wasn't necessarily terribly convenient. We'll learn about the moment area method, the conjugate beam method, even a little bit of virtual work. There's some other techniques out there all along the way that we'll learn, and we'll be learning some computer modeling to go along with all that too.